Thank you. Yeah, so I am a postdoc in statistics at the University of Copenhagen, and I do probabilistic genotyping from a statistical point of view and not from the case point of view. And I have 3 main points today, 3 take-home messages. And the main one is that rather than trying to target a particular question for use in a court case, I really just want to build a system, a framework, and an actual implementation that gives a user the possibility to work with DNA mixture models as for any other model. So if I give you a linear regression model, you can do some things. You can fit some models to your data. You can do some predictions. You can compute various quantities. You can make some graphs. That's what I want to provide for DNA mixture models. And to do all of that, I propose to use a statistical framework. So simply, we start off by a statistical model, and then we can throw all sorts of statistical methodology at that. And one of those things is statistical model checking. So I'll be talking a bit of some methods that I've proposed that we can use in both checking the model in a particular case or do validation. And my third point is that it actually pays off to do some more core development of computational methodology, because as Roberto was just talking about, there are some huge barriers that we all run into regardless of the model that we use. So I try to target those in a more fundamental way. Right. So just very briefly, what we're looking at, DNA profiles using STR markers. A marker is just some place on the chromosome that we can actually identify, and the allele is the actual sequence that is found at that marker. The STR markers are chosen a particular way. We all have the same at the ends here. That's how we find the region. And then we vary in what we see here in the repeat region. And that is, as Roberto just explained, we have a different number of repeats of a particular word. And there might also be some more detailed variation, but usually we can't see that in the measurement process. So we have 2 alleles per marker because we have 2 chromosomes. And the pair of alleles in not any particular order is called the genotype, and the DNA profile that we map is the set of genotypes over all the markers. So how do we measure that? We never actually read the sequence. We just get an electropherogram like this, EPG. And here we sort the alleles, or we register them by how long they are. So the x-axis here is the length of the allele, and the different panels here are different dyes. So some markers, for instance this marker, has a range of alleles of length something to something, and another marker here has alleles of the same range. So we use different dyes for them. So if you tell me which dye or which color the fragment is and how long it is, I can tell you what allele the person has. The peak heights, they represent how much of that particular allele is in this DNA sample. And the standard is to say that the peak height is proportional to how much DNA there is of that particular type. And it's not quite as simple as reading off the EPG, because there are various artifacts that Roberto also just talked about. We can have peaks that shouldn't have been there, but they're there nevertheless, and peaks that shouldn't have been there, that should have been there but aren't there. Right. So I will talk about DNA mixtures as basically any sample of DNA. I don't really care if it is from one or more people. So for me, a DNA mixture is just a sample of DNA from some number of contributors. Usually I don't know the number of contributors, and that's what we were discussing in the discussion session yesterday. we can all have our own little hypothesis of the contributors to this DNA mixture, and this is essentially what the main inference is about. We have a DNA sample. Who left the DNA sample? Or to whom does this DNA belong? So a hypothesis I would think of as my personal explanation of this mixture in terms of a set of potential contributors. So I claim that these are the people, but they might or might not be in the real world. And in this we always distinguish between two types of contributors. Known contributors where we know their full DNA profile, so we know which alleles they have. And then unknown contributors that are kind of placeholders, where we say this is a person from a particular population. And then we would use some distribution of alleles from that population to have like a prior on the genotypes for that person. So what I want to propose, and is actually also usually the way people specify models, is to make a model for the DNA profiles and that you cannot observe, and then the p-kites that you can observe. And I want to do this because then I focus on modeling my system rather than targeting particular questions. So two particular questions I do want to be able to address for this to be useful is the two most commonly discussed questions in casework. So one is compute the likelihood ratio of two proposed hypotheses. And the other one is deconvolution, where I start off maybe with no information and I just want to say something about the contributors to this sample. What might their DNA profile be? So what I do is I model the system rather than addressing these two questions directly. And then I want to use the system to address them. And the point is that I'm using the same framework, the same model for my system in targeting any question. And therefore I get some sort of self-consistency because I'm not claiming something new about the measurement process for each type of question that I'm answering. Right. So the model looks like this. So this is for a given hypothesis and a given set of model parameters for the measurement process. I look at a statistical model for all the genotypes of the contributors that are in the hypothesis and all the p-kites that I observe in my EPG, or maybe many EPGs if you have replicates, or for some other reason more EPGs. And the probabilistic genotype system that I have made, DNA mixtures, the R package, is simply an implementation of this statistical model for a particular p-kite model. So the usual way of specifying such a joint model is similar to what Roberto was talking about. We have, so it splits up, this is just the normal conditional independence, splits up into a model of, given all the genotypes that are in this DNA sample, and maybe some model parameters such as, importantly, the mixture proportions, the proportions in which the DNA has been mixed. Then what can we say about the p-kites? So this is a distribution that describes the measurement process. And the second part of this model is, given the hypothesis, what distribution does the genotype have? Or do the many genotypes of the contributors have? So this is the one that usually uses population frequencies. So one of the main things to compute in this framework is the likelihood function. We use that for pretty much everything. And that is, in principle, simple. We take the joint model and we sum over all the possible genotypes of the contributors. So this is a sum over all the genotypes that the unknown contributors could have. So that gives us the marginal distribution of the peak heights that we can observe. So that's the likelihood function. And the problem is, as we add in more unknown contributors, we get a really big sum here. So that's in practice difficult to compute. And in the paper that Roberto was referring to, Steph and I have been working on actually computing this exactly for a given peak height model. So, can I actually address the questions that I want? Yes. I can compute the likelihood, so the likelihood of seeing this EPG given any hypothesis and any set of parameters. So therefore, for any two hypotheses you give me, of course, I can also compute the likelihood ratio. And for deconvolution, that Roberto was also talking about, if we have a joint model for the peaks and the genotypes, we in particular have a posterior distribution of the genotypes given the data that we've seen, and we can look at the posterior most likely sets of genotypes and go about doing deconvolution in that way. Yeah, so we discussed that a lot in an informal seminar a couple of weeks ago. So to do this sort of thing, we would have some background information, maybe think that the unknown contributors, there could be maybe two of them, and they are of, I don't know, UK Caucasian descent, and then given that information, what is then the distribution? What are the most likely genotypes? So we would first formulate some sort of hypothesis about that. Right. So in this framework, I like to distinguish quite a lot between four things. The first is the particular statistical model I use. So I haven't told you what model I like to use. I've just talked about this in a very general way. But in a particular case, I will need to describe to you exactly what that model should be. The second thing is how I then use the model to answer the questions that I might get. That could be, I address deconvolution by looking at the posterior most likely profiles. And that's completely independent of what model I'm actually using. The third point is how I then go about computing stuff. Again, that has in principle nothing to do with what my actual model is. So I can develop that separately. And then the fourth point is the software I go ahead and implement, because there I make some choices and limit myself to maybe a particular model and a particular strategy for estimating parameters and so on. Right. So a really big benefit of this statistical framework is that it allows me to just use a lot of statistical theory on DNA mixture questions. And one big thing that I like to push for is that we should challenge a model when we fit it to data. I call this challenging an interpretation of the mixture. So by an interpretation of the mixture, I mean roughly these four things. Some hypothesis that characterizes what contributors I have in the sample. And closely related to that, the assumptions on the distribution of the genotype. So any unknown contributor, I would need to specify my model assumptions for those. So I could specify those by saying I use the vanilla basic model for unknown contributors, saying they are all independent and unrelated from a particular population, perhaps the UK or US Caucasian population. Then I need to say which model I have used for the measurement process, so the peak height model. And I could take my favorite model, because this is the one I've been involved in, but I could also take maybe any other one, the Roberto's or David's. And I claim something about the parameters as well when I do an interpretation. This is maybe saying something about in which proportions the DNA is mixed, or how much stutter there is, how much drop-in there is. All these parameters, they are part of an interpretation of the sample. And one way of inferring them could be by maximum likelihood under the particular hypothesis. So all these ingredients give me an interpretation, and I can form my own, and you may rightly ask, so is that interpretation any good? So this question can be asked at many levels, and the one I'm talking mostly about is maybe a little bit new, in that we shouldn't just focus on validating a particular system. We should also address the particular interpretation that you make in a case to make sure that all these 4 ingredients are actually meaningful and describe the case well. So once you have a case, you should do some model checking. And I can do that by systematic methods because I have started off with a statistical model. So some examples for why this is relevant to a particular case is also something we actually discussed yesterday in the discussion session. If we calculate a likelihood ratio, we might get something that looks really discriminative, but what if neither of the 2 interpretations are any good? Then, I mean, yeah, one is better than the other, but they might both be really poor. And there could be many reasons for a poor fit. Maybe I have a bad p-kite model. Maybe I don't do enough degradation. Maybe my stutter model is wrong. There could be many things, but we can then go and investigate that further. Maybe the model for the unknown contributors is unsuitable. If I actually have an Afro-Caribbean person, maybe using the UK Caucasian frequencies is really unsuitable, and that would show up in a model checking method. And then there could also be some simple things, like I thought that the stutter filter wasn't on. I got the data, and there was suddenly a lot of stutter. So that would show up in model checking methods as some sort of outlier. Similar with errors in data. I mean, maybe someone just typed in the wrong peak height. Silly things can happen, and these things can also be caught in the sanity checks that model checking is. And an important thing to note is that we can use the same sort of argumentation and probing interpretations when doing validation studies, because what is a validation study? I take a lot of DNA mixtures where I know what I put in. So this one person or these 2 people in this particular mixture ratio with these particular genotype, and I want to see, does the model capture stutter well? Well, I can address that directly, systematically. So the idea of statistical model checking is evidently not something I came up with. The overall idea is that if you give me a model, I give an interpretation of the DNA mixture, I can take what I observe in the sample and compare it to what the model claims I should see, or how it should vary in the model. And then we can probe these assumptions in various ways, and sort of 2 overall branches would be, one is by looking at various graphical methods for diagnostics. These can be really helpful, especially in communicating and interpreting in what way the model fails, if it fails. And another one is statistical testing. So where you get more like you get a p-value saying, is this fit good or not? Or tests along the line of saying, well, is there degradation in this sample or not? Well, if the degradation parameter could be assumed to be 0, well, maybe I don't need to model degradation in this particular sample. And you can reason in that way by statistical methods. So here's a specific example. I have fitted a model. I'm not going to tell you what. But I have a hypothesis here with 3 known people, so I know these 3 profiles, and then I have some unknown contributor with, incidentally, very little DNA, so essentially I know what goes in this mixture. And I have 3 markers, and I've drawn the EPG, and for each peak I have indicated the 99% prediction intervals. So the antennas here are the 99% prediction intervals. There's the median and the 2 upper and lower quartiles. So we can try to look at how my particular interpretation explains these data. And we can go and see, well, maybe that, if we look just at the bigger peaks, this one is a bit low. It's well below the 25% quantile. It's a little bit low here. This one is a bit extreme, but extreme high. You could go in and investigate. Let's look, for instance, maybe at... So I've indicated here that one of the people, K3, that I've now assumed in the mixture, he has the allele 20, and this little allele is bang in the middle of the distribution that I claim it has.
What's the uncertainty in that distribution based on what information?
In this case, it is conditionally on... It's the distribution of a peak given all the other peaks in the EPG. I think, but
and all the fitted parameters.
Yes, yes. So what I'm showing you now is for a fixed set of parameters. In this case, I've inferred them by maximum likelihood.
Sorry, can I just also ask?
Yes.
The black bar's probability of no peak, I mean, that's just, do you mean no allele? Because, I mean, a peak is just an observation, yes or no?
Yeah, no. So probability of no, the probability of not seeing a peak.
Distribution, yeah, okay,
Yes.
I see.
So I'm only looking at posterior predictive distributions here and say, for this allele, allele 10, do I expect to see a peak or not?
Yeah.
And here I expect everything to be under the threshold. Whereas for this one, there's a 50% probability of not seeing a peak and a 50% probability of seeing a peak.
But seeing a peak means seeing
above
Seeing it above threshold.
Above.
Yep. So if I change now the hypothesis, I say maybe K3 is not there. Maybe it's just some unknown person. Then I'll go back and forth. This is with K3. This is without K3. You see that I get a bit more uncertainty here, because I now have an unknown contributor, and he could, in principle, have any of the alleles with some distribution. And if you go back to look at the allele 20, we can see that seeing a peak here is actually now quite extreme. The probability of not seeing a peak has gone up a lot, and we are now more in the tail of the distribution. Let's see. So this is a nice scale, I think, to look at if you're used to looking at EPGs, because it's the original scale. But it's more difficult to get a feel for sort of jointly how extreme are my peaks. Of course, if I have, I could make tests like saying, well, I would expect 50% of my observations to lie within the 50% middle range. Of course, I need to be a little bit careful here because the intervals are not independent here. But so I can also transform the peak heights to a uniform scale. So here I make use of the fact that if I take a continuous variable and I transform it by its cumulative distribution function, I get a uniformly distributed variable. And my peak heights, given that I've seen them, so given that they are above threshold, they are indeed continuous. So I can now make a check, sort of a joint check of all my peak heights and see whether they are extreme in any way. So if they're distributed as I claim they are, we should see a straight line here, a diagonal. I guess there's nothing particularly untoward here. Maybe that's a bit better than the other hypothesis here was a bit crooked. But we also don't have too many points. I can actually make these points independent if I look at the right distribution. So here again, here I've been looking at the distribution of a peak, not given all the other peaks, but I can look at various distributions, posterior predictive instead. So this only looks at whether I captured the actual height of the peaks that I see in the EPG. So of course that doesn't prove that I'm good, because what about all the peaks I didn't see? So can I correctly predict what peaks that I actually see in the EPG? So now if we look at all the allelic positions of the EPG in some order, so I've introduced an order, it's arbitrary, but I need to decide some order. So let's say we look at it from the left top panel and just go along one position by position, and in each position we can see a peak present or absent. And I introduce a penalty. I say, well, if what I actually saw was really unlikely, according to my model, then I give it a huge positive penalty. And if I said that what I saw was really very likely, I just give almost no penalty. Of course, I also expect to be wrong sometimes, so there's an expected penalty. So I look at the difference between the penalty and what I expected. And we plot this in a frequential monitor. So Philip David can tell you much more about this frequential framework. But you'll see that in the penalty here, I'm looking at the probability of seeing a peak given all the peaks that I've seen up until that position. So the order does actually matter here. All right, so here's an example. So from what I said on the previous slide, I get a huge jump upwards if my model is quite wrong, if I'm guessing for the wrong event, and I get a jump downwards if I'm correct. If there was only one possible choice, I get nothing for guessing it correctly. So that's why we get a lot of straight lines here. Horizontal lines. Okay, so what do I have here? So I've laid out all the peaks in my EPG here. So that's like the first panel, 4 markers, the second panel, 3 markers, I think, and then the fourth panel, third panel, sorry. And then that's because then we can see in the top one, whenever there's something weird going on here, I can go back and look at my EPG, why maybe something is off. So here I flagged in red every time we get a jump upwards. So no particularly huge jumps. We can see that we stay, so these are asymptotic upper prediction limits. So if we stay under those limits, our model is adequate. But here I get a jump. You can see I get a jump up at 14, allele 14 on the marker D8. And I can go down and see, oh, I'm actually surprised that I saw a peak from K2. So K2 is a very minor contributor, so I could go in and investigate why am I surprised, maybe, I don't know what would be the reason. There's another big jump here for allele 9, and if we go down to allele 9 here, the person K2 that I proposed was there. He doesn't show up with an allele, so the model says I would have expected to see a peak, but I didn't. now let me do the same as before. I propose that K3 is there. What if he isn't? Oops, then we get a lot more jumps. And again, I flagged all the upwards jumps because those are the ones we're wary about. And if you look at the downwards, or the lower panel, every time there's an allele that K3 could have explained, I actually get a jump upwards. So, this isn't necessarily a cause for worry. It's simply because now this unknown contributor has to explain all the alleles that K3 could have explained, and it's fairly unlikely that an unknown contributor has exactly all those alleles.
Very quickly you said, what are the dotted and dashed lines again? That,
the 95 upper prediction limit and the 99 upper prediction limit. So we can see that this potential monitor does wander off. So you may claim that maybe it's not actually fitting very well, the model, at least for the first set of markers. But overall, if we look at the whole EPG, the model is fine because we end up under the limits. So this is an asymptotic result for the variability going to infinity. So what happens just at the beginning, we shouldn't take too seriously. But it's very clear that, well, this model fits better. All right, so just for fun, I've removed one more unknown contributor. That makes it even harder for the model to explain what I've seen. And now we actually end up outside. So we can see that the claim that there are just 3 contributors is bad in this case. Going back to these probability transforms, what could we use them for? Maybe in validation, we can investigate things like, is there a difference, is there any sort of trend in the EPG that my peak height model doesn't capture? And one could be, maybe there's a different scale for each die. And so here, maybe my yellow die peak heights are a little bit too low than what I should have got, because I should have got something that's uniformly distributed here, 0 to 1, and I don't really. So what if I change and allow different parameters for each die? I get something that looks better. So this is a good way of both probing a model and also to suggest in what way I could improve a model. And I could also investigate further into the EPG. Maybe there's some trend over markers, maybe some trend over fragment length. Maybe that we see a slight downward trend here. Up here for D2, there's definitely something fishy going on. They're way too low, these points. And I could go in and see why I haven't for this one. Right. So a few final words on the actual implementation and the computation bits. So I implemented this in the R package. So it's essentially just an implementation of a big statistical framework, statistical model, where I can exactly evaluate the likelihood function and all the other quantities that I compute. So marginal distributions, conditional distributions, quantiles. I can do simulation. And then, so this is like access to a statistical model, and then I've implemented also some particular statistical tools, like the ones we've just discussed. And we can infer parameters by maximum likelihood with arbitrary constraints. This is nice because it means that I can also do things like profile likelihoods. So, the computational approach is that I really do want to avoid approximations if possible. And it is very, very common, because this is so computationally intense, to introduce some sort of heuristic measures to limit the number of genotypes that we consider when doing these huge sums. So I worked for a very long time, very hard on this, and gained some progress, as Roberto was also talking about. And my overall strategy has been to find some good way of representing the whole model as a Bayesian network, because that means I can throw a lot of well-known techniques for Bayesian networks at my model. And things that these techniques, especially probability propagation, is really good at computing is various marginal distributions in the network, various conditional distributions, and in general sums over the entire state space. And this last point is what I'm going to show you a slide on. I will stop in a bit. So here is the genotype representation that Roberto was referring to. I start from the other end that we did in the last workshop. I know exactly what model I want to represent by network. So my problem is not piecing together a network, but rather making a network that does represent that model. And the vanilla model for genotypes is that a person has 2 alleles sampled from a multinomial distributions with frequencies as in some population. And the thing to know is, so here are 6 alleles at a marker, and rather than telling you that this person has allele 2 and 4, I can also tell you that he has 0 of allele 1, he has 1 allele 2, 0 allele 3, and so on. So I've now introduced a lot more variables, but the point is that I can allocate these sequentially. And so in allocating how many alleles of type A that the person has, I only need to know how many alleles I've already allocated, therefore how many I have left to allocate. So this network is actually really simple because these S nodes are simply sum, so S3 here is just the sum of how many alleles I had left to allocate, or I had already allocated, and how many I just allocated. And these arrows are binomial distributions. And I can also express more complicated models in the same way. So this is the total vanilla model. And the peak heights can also be represented in the network, and we still keep this local sort of computation because the peak heights will only depend on, the peak height at 3, say, will depend on how many alleles a person has of allele 3 and of allele 4, if we consider just one type of stutter. If we do as Roberto does, we extend this, and it becomes more complicated. And okay, I have 2 slides to give you. The whole point here is that Bayesian networks give me a representation of the joint distribution of all my network variables. And propagation can really give me 2 very important things. If I propagate information of any of the variables, it gives me the conditional distribution given that information, and really, really importantly, it gives me the probability of the information that I have propagated. And I'll finish with this nice little theorem. It means that, much more generally, if I have a network representing the distribution of some variables x, and I propagate information h of x, then as a byproduct of the probability propagation, I actually get a sum of this function over all the possible states of x. And that is exactly what I want if I compute things such as the likelihood function. I want to compute here the marginal distribution of peak heights by summing up over all genotypes for the peak height distribution given genotypes. So one single propagation will give me the likelihood function. And I'll end there. Thank you.
Very much, Therese. May I ask the first question?
Yes.
So does that mean you have to do a new propagation every time you decide to compute something else?
Yes.
Yes. Okay. Phil.
When you were assessing the distribution of a peak height conditional on all the other peak heights, were you using anything like the outpropagation algorithm to do that simultaneously?
No, just what normal propagation.
So you did it. You had to do a new propagation for every peak height.
Yes,
Because Robert Carroll and I had a method where we could do it simultaneously.
I do a new propagation, yes, but I'm using Huyen, and it does only propagate sort of locally in the network. So if I change the information, the evidence on one node, I only need to repropagate sort of locally. I'm not totally into the details of how it does it, but I don't need to do the actual full propagation every time. But it would also make sense to do the simultaneous one.
Yeah.
I should look into that, yeah.
Yes. Okay.
So you have quite a number of parameters, and you do then maximum likelihood estimation. Do you have any numerical problems with that, especially when the model doesn't fit well?
No, I haven't had it. So the model here is, the number of parameters is kept to a minimum. And therefore it actually goes really well, the maximum likelihood. I've worked on introducing degradation as well, and there we start to see some numerical instability. It might just be numerical instability, it might also be that there simply isn't enough information. I'm unsure. It seems to always go well. I mean, the only problem I've encountered with maximization is all these local modes that you naturally get because your likelihood is symmetric in the unknown contributors. So it's very difficult to ensure that you find the right maximum. So you really need to start the algorithm from many places and make sure that you get the highest mode.
More questions? Yes.
Well, so one of the issues when you're just searching around in genotype space is that traditionally we've done this. So you search around in genotype space, typically, as I understand it, many software such as yours and NCMC type ones, without knowledge typically of the suspected contributor's genotype, and then at the end you then see what probability is assigned to that genotype. Is that what you do in effect? Or you don't do separate runs under competing hypotheses, do you? You fit one model.
No, I would do it per hypothesis.
Oh, you do it separate
Yes.
for each hypothesis?
Yes.
Okay.
And I don't really need
When
to
you talk
search
about
the
the-
genotype space because what the probability propagation will automatically consider all the possible genotypes.
Sorry, I understood when you talked first about the unified framework, I thought that you would did all just one analysis.
Sorry, yeah, no.
Certainly some software does that, but yours doesn't. Okay.
Yes, no, it's unified in the sense that the way I specify things is the exact same, but your hypothesis is, so to say, a different parameter so that you set. So it's the same way of specifying it, but you specify two separate hypotheses, and or however many you want to specify.
Okay. So what I was getting at really was that traditionally we've done this population genetics correction, which sort of favors the defendant in a way by biasing upwards. You can think of the frequency of the suspected contributors' alleles.
Yeah.
And so, do you have that in your framework? And
Yes.
Yes.
Yeah, I mean, so various things. So when I do this network, all these little arrows in that is hidden a binomial distribution that depends on genotype frequencies or allele frequencies. And if you want to correct them with the FST, you can just do that in advance.
Okay.
So that's not a
okay. So you do the correction in advance rather than it doesn't somehow. Yeah. Okay. It doesn't.
So you can include the parameter.
in the calculation, but, okay. Anyway, that's fine. Thanks.
Or you can use various models, but that's just the most simplistic way of doing it.
If you do deconvolution, so identifying or listing likely genotypes of unknown persons, then there must be some searching involved. Or not?
Yes, the way yes and no. So the way I look at posterior most likely profiles, and I identify, say, the 7 best genotypes, and their profile and the probabilities are exact. The way I find them is actually by simulation, because that's the most easy way of doing it. But if I ask the computer to give me all the profiles with posterior probability over 10%, it will give me all of them. Yes.
I guess, I mean, you can check afterwards you found them because you're going to add the probabilities up.
That's it, yeah.
And if you know what's left, the residual probability is smaller than the one you have, then you have the maximum. But it's not sort of like a heuristic search.
No.
You know after you've done it whether you found it or not.
Bill, last question?
You mentioned various challenges to interpretation, I mean, things that could be wrong with the interpretation, and then you went on and talked about various model checks to see how well the model fit. And I guess what I'm wondering is can you make inferences about the former from the latter? I mean, by looking at the way in which the model fails to fit, can you infer back as to whether the problem is an incorrect hypothesis or incorrect assumptions about genotypes, or or is that something that needs to be explored empirically to determine what these failures to fit might mean?
It will depend on the way the model fails.
Yeah.
So of course, I mean, if any of the things fail, you would maybe see something wrong in the final plot. And you may go back and do multiple plots to see if you can narrow down the specific reason. And I guess sometimes you won't really be able to distinguish, but maybe sometimes you will.
Okay.
I mean, things like like if you use the wrong database for, well, it's very difficult to say whether you can distinguish, like, to see if you use the wrong allele frequencies. Yes, you would often be able to narrow that down, but on the other hand, if you also specified the wrong set of contributors, wrong number of contributors, I don't think necessarily you can. I don't think you can say anything general.
Okay, so it doesn't allow the kind of differential diagnosis that would allow you to say exactly what's wrong.
It does if you investigate enough. Yes, it does. You can make a good explanation of why things go wrong, but you can't prove it that this is the reason.
Fair enough.
Okay, I think we stop now and thank both the speakers.